Okay, so suppose you have a thumbtack company and you want to test your thumbtacks. And in particular, we know that when we drop a thumbtack on the ground, it's going to land, ultimately come to rest in one of two positions. We're going to have a position that we call danger that would really hurt if somebody stepped on it. And we have another position called safe. That would still hurt if you stepped on it in your stocking feet, but not quite as bad as danger. And what we are interested in is if a thumbtack falls off the tabletop, lands on a hard surface, what is little p, the probability that it lands in the safe position. Okay. Now, we can do an experiment. We can drop many thumbtacks on the ground and see what proportion land in the safe position. That's going to give us an estimate of p. P hat is our estimate of p. By the way, just as an aside here, p with an apostrophe after it, pronounced p prime, is your textbook's notation for the same thing. So I just want you to recognize, if you're reading the book, that there are books going to be using p prime to stand for the same thing I'm going to be using p hat for. So we drop 800 tacks on the ground, and 556 land safe. Okay. Well, what we can calculate from here is an estimate of p. P hat, our formula, x over n, in this case, number landing safe over number dropped. This is 556 over 800. We get p hat equal to 0.695, I believe. And let me check that on my calculator. I'll give you a moment to do so also. So we'll get the timing right on this. So take your calculator, and 556 divided by 800 is indeed 0.695. Okay. While I'm at it, I'm going to find Q hat, which is 1 minus P hat, which is 1 minus 0.695. I will get Q hat is 0.305. Now, all we have is this one experimental result. And the number that we've got here, P hat, is an estimate of P. There is some true value of P. That's the overall probability that a thumbtack lands in the safe position. And we will never know that. You'd kind of have to toss millions and millions and millions of thumbtacks to really be confident that you knew P. P hat is our estimate. And our estimate based on our experiment is that the proportion of times that a thumbtack lands safe, or we could also say the probability that a thumbtack lands in the safe position, is 0.695. Now, if we had many, many examples of this experiment, I sent everybody in the class, okay, there's nobody in the class right now, but if we sent everybody in the class home with a box of 800 thumbtacks, said drop these all on the ground, and then count how many land in the safe position, we would not all get the same result. We'd probably have close to the same result, but we wouldn't have all the same results. So again, this is an estimate of P hat. We'd have a bunch of different estimates of P if everybody did the same experiment, but we wouldn't all necessarily get the exact same result. Okay. P hat is called a point estimate of P. If I had a number line, I've got 1 point on my number line right here. This is a point on the number line that we're using to estimate P, hence the name point estimate. 1 point on the number line that we can use to estimate P. All right, that's simple enough and something a grade school person intuitively might have figured out. If they want to estimate P, do an experiment. What we're going to do and get progressively more sophisticated about as we go along is we're going to make an interval estimate. That is, we're going to take our point estimate and we're going to say, you know, this might not have nailed P dead on. I know that because I know if we did several experiments, we'd have a bunch of different values of P hat. They can't all be correct. Only one of them would be at most correct. So what I'm going to do is I'm going to make an interval. I'm going to go up a little ways and I'm going to go down a little ways. Perhaps I'm going to go up 0.04. Is that showing up big enough on the screen? Not quite? Okay. I'm going to go up 0.04 above and 0.04 below and get an interval, a chunk of the number line, an interval, and I'm going to say, you know, I'm not exactly sure where P is, but I'm pretty sure that it's in here. So these points are going to be, here's my point estimate. Point estimate at 0.695. Here I'm going to have 0.695 plus 0.040, just to keep the decimal points the same. Here I'm going to have 0.695 minus 0.040. So this will be 0.655. This will be 0.735. That's my interval. And I'm going to say, I think P is between 0.655 and 0.735. Using interval notation that you learned, hopefully. back in your algebra class, it looks like this. And I'm not going to use hard parentheses because these are all just estimates. So we're not going to use square brackets here. We're using round brackets for our interval. And I miswrote. I don't know why. That's 655, not 635. Okay. Now here's the point where I usually ask the class questions on that, but can't get it. This choice of 0.04 was somewhat arbitrary. I'm going to use capital E to stand for my maximum likely error estimate. Book calls this EBP for error bound for my proportion. Okay. So two terms that are somewhat interchangeable here, proportion and probability. What's the probability that a dropped thumbtack lands in the safe position, or what proportion of the time will thumbtack land in the safe position? Those are going to be interchangeable. And again, in terms of notation, I'm going to be using just capital E for error, but your book uses EBP to stand for error bound for proportion. So just to get down the mechanics of making an interval estimate, I'm going to put a couple examples up on the board. And my choices for E at the moment are somewhat arbitrary, kind of choosing some extremes to make a point. But again, I'm a little bit arbitrary here on my choice of E. So we already saw if I let E equal 0.04, my interval estimate, I'm going to erase more board here because I want to keep this all on one line here. My interval estimate, which is p hat plus or minus E, is going to be 0.695 plus or minus 0.040, which is 0.655 to 0.735. Let's suppose instead, if I let E equal 0.20, my interval estimate p hat plus or minus E is going to be 0.695 plus or minus 0.200, which is 0.495 to 0.895. And I'll do one more. If I let E equal 0.002, my interval estimate p hat plus or minus E is 0.695 plus or minus 0.002, which is 0.693 to 0.697. Okay. So again, my choices of E at this point, somewhat arbitrary. I just wanted to get down the mechanics of how we make our interval estimate. This symbol you've seen before, I'm sure, when you were doing the quadratic formula and maybe other places. We verbalize this, we call it plus or minus. But when I'm doing these numbers, intervals, we usually go smallest to largest. So these I was able to do in my head, but if your numbers are a little bit uglier or you're not as confident doing it in your head, do the subtraction first. So 0.695 minus the 0.04, and then 0.695 plus the 0.04. We do the subtraction first, so we get the smaller number first because we want our intervals to go from smallest to largest. 0.695 will be right in the middle of all of those intervals. And I went 0.695 up a little, down a little ways, and then up a little ways to get my interval and say, so here's what I'm saying. I'm trying to find P, the true probability of a thumbtack landing safe. I'll never know what P is, but I'm going to try to estimate it. My first estimate, called a point estimate, was P hat. 0.695 was my experimental result. This is also what you get. You have P hat, you have an estimate of P when you do a survey. So in an example that I did on the document that you were passed out, we asked California adults, do you think Gavin Newsom's doing a good job? And you had there a P hat of 0.585. Again, that was 1,200 people out of the entire adult population of California. In this case, we have 800 thumbtack drops. If we wanted to be really, really, really confident we were precise, we'd have millions of thumbtack drops, but we don't have the time or the energy to go out and do millions of thumbtack drops. So we've got our intervals here. And what we're saying is, I've got an interval, and I think the true value of P lands in this interval. Now, what I want to point out here is what happens when we make E too big or too small. First one's a pretty good interval, actually. If I made my error estimate really big, 0.20, I am very, very, very sure that the true value of P sits inside this interval. But this interval is so big, so sloppy, it doesn't really give me a good picture of what the true probability is. I'm saying roughly that thumbtacks are going to land in the safe position somewhere between 50% and 90% of the time. A little bit different, but close to 49.5% and 89.5%. That's such a wide range, I'm not really conveying any useful information. It's kind of like saying if we took the average height of all women in California, the average would be somewhere between 5 feet and 6 feet. Duh. Okay. Yes, there are some women smaller than 5 feet. Yes, there's some women taller than 6 feet. But we certainly know the average is between 5 feet and 6 feet. That's such a wide interval, it's obvious without taking any data. Well, this interval's nice and tight. But what I'm trying to do is I'm trying to say what the true value of P is, and this is a nice, tight, precise little interval, but I'm not so sure that P truly lies inside that interval, because I'm not very confident that my experimental result, my point estimate, is this close to the true value of P. I've got an estimate. I hope it's close to P, but I don't know for sure. And I can't really be extremely confident that we're this close to P. This actually is the most reasonable of the three. My interval's not so wide and sloppy that it doesn't convey any meaningful information, but it's not so narrow that I'm not so sure it's right. Okay. What we're learning to do in this first part of Chapter 8 is to make good estimates of E to get good intervals. And we're not going to just say, hey, here's my interval, and arbitrarily grab values for E like I did. We're going to calculate good values for E. And what we're going to be learning to do is we'll learn to make a 95% confidence interval for P, or maybe a 90% confidence interval for P, or a 99% confidence interval for P. These 95% confidence intervals are by far the most commonly used. 90 and 99% are next. We could kind of make whatever we wanted to. I could make an 88% confidence interval, or a 50% confidence interval, or a 99.99% confidence interval if I wanted to. What we're conveying here, what we're saying is, I'm not just giving you an interval, I'm telling you how confident I am that this is right. And these numbers aren't arbitrary. We're going to calculate our E in such a way that it will give us an interval, and mathematically we're 95% confident that that interval is right. That is, we're 95% confident that the true value of P falls inside my interval. Okay. If I want more confidence, I can get it. I can make a 99% confidence interval. But what's going to happen is I'm going to have to widen my interval to gain that extra confidence. So there's a trade-off here. If this is a 95% confidence interval, I've got to widen it to be more confident, to make it a 99% confidence interval. Again, here's my 95% confidence interval. I want it tighter. I can make that interval tighter. Not that ridiculously tight, but I can make it tighter, but there's a compromise there. Maybe I'll only be 90% confident that that interval is correct. Or tighter still, but now I'm only 80% confident that that interval is correct. So there's a trade-off as we gain confidence with the same data set. In order to gain confidence, I've got to make my interval wider. Okay. So, how do we do this? Somewhere out there, there is a true value of P. And I don't know what it is. If I did, I wouldn't have done that experiment in the first place. Or if you knew what proportion of voters liked your candidate, if you knew the whole overall proportion, you wouldn't bother doing a survey. But we're trying to estimate the proportion. Somewhere out there, there's a true value of P. And if we had not just my one experiment, but many, many people all going out and dropping 800 of these thumbtacks, we would have a bunch of values of P hat. And those values of P hat would be normally distributed. At the center of the distribution would be P, which deserves a z-score of 0. So your experimental result has a value of P hat, and it deserves a z-score. And if your experimental result, your P hat, hit P dead on, your experimental result deserves a z-score of 0. If you had a few more landing in the safe position than usual, you would deserve a positive z-score. And if you had fewer, your experimental result would deserve a negative z-score. Again, if I had a lot of people do this experiment, I had a lot of people each go home and drop 800 thumbtacks and come back to me with a p hat, we'd have many, many values of p hat. And if we plotted them all, we'd have a bell curve. We'd have a bunch of people getting p hats around here in the neighborhood of p. We'd have some getting higher proportions, not that they did anything right or wrong, just luck of the draw, luck on their experiment. They got a higher proportion landing safe. And some people would have a lower proportion, and most people would be pretty close. And we'd have a distribution like this. Now, we don't have many, many different values of p hat. We only have our 1. And we don't know where p hat belongs on this scale. We don't know what kind of z-score our p hat deserves. But if I take us back to the second week of class, when I've got a normal distribution, I know that 95% of the time we get a z-score between -2 and +2. We know that 95% of the time we get a z-score between -2 and +2. So we know that our value of p hat, which was 0.695, probably missed p, but probably didn't miss it by more than 2 standard deviations. 95% of the time, it's going to miss the true value of p by less than 2 standard deviations. So 95% of the time, the true value of p will be within 2 standard deviations of my p hat.